Okay, let me go ahead and start. So my name's Steve McBride. I'm the secretary in the Western Australian section. Good morning or good afternoon, wherever you happen to be in Australasia right now. And it's my pleasure to be the moderator of this meeting and introduce Audrey Mascarenhas today. She's the president and CEO of Questor Technology. The title of today's talk: Is there a future for oil and gas in a net zero world? And you will see the SPE Gaia Sustainability Program logo on Audrey's first slide. So this really ties into that new program. And at the end of the presentation, I will be asking a couple of questions via poll about that. So let me introduce the talk. Our industry is facing mounting pressure from all sides to decarbonize. Regulations are getting tougher in response to public pressure, and investors are pulling capital out of the oil and gas industry over concerns that assets may be left in the ground stranded. Natural gas has been touted as a transition fuel to net zero. However, because of the methane emitted in the production and distribution process, some believe that it is dirtier than coal and cannot play this role. We have to act now, or our industry will be viewed adversely, and collectively, we will make poor energy decisions for our planet. Technology that is able to detect and measure methane emissions is showing that we have a problem along our entire exploration, production, processing, and distribution chain. According to the World Bank Global Gas Flaring Reduction Group, every day over 14.5 billion standard cubic feet of gas is vented and flared globally. In addition to being a monumental waste of energy, this practice releases methane, VOCs, PAHs, particulates, and other harmful pollutants into our atmosphere, impacting air quality, human health, and contributing to climate change. Methane is 86 times worse than carbon dioxide over a 30-year time frame, which means that eliminating these fugitive emissions is one of the biggest opportunities to cost-effectively reduce greenhouse gas emissions, providing an immediate impact in a short time frame. Can we act? Do we have time to change the narrative? And can we create a great future for all? What will it take? So Audrey Mascarenhas is president and CEO of Questor Technology, a public international company focused on clean air and energy efficient technology. Audrey has worked in energy and environment for over 39 years with Gulf Canada Resources, currently called ConocoPhillips, and now with Questor. Through her leadership, she is focused on technology solutions to eliminate methane and harmful pollutants. Audrey shares her passion for the environment and served as a distinguished lecturer with the SPE in 2010-11. She is a graduate of the University of Toronto with a bachelor's degree in chemical engineering and holds a master's degree in petroleum engineering from the University of Calgary. She is a fellow of the Canadian Academy of Engineers. Audrey was also the recipient of the Ernst & Young Entrepreneur of the Year 2011 Prairies Award for Clean Tech and Environmental Services, and received a national citation for values-based innovation. Audrey currently serves as an expert on the Circular Economic Panel advising Environment Canada, the Lazaridis Institute Global Advisory, and the Schulich Industry Engineering Advisory Council. She chaired the Canadian Federal Government Clean Technology Economic Strategy Table and was an Energy Futures Lab Fellow. So just before Audrey starts, if you want to ask a question, you're welcome to type it in the chat box, and you can also ask your question verbally at the end of the talk by raising your hand. So I'm delighted to introduce Audrey to give us this inspiring talk. All yours, Audrey.
Thank you so much, Steve. And everyone, it's a pleasure to be here. What I'm hoping to do is talk a little bit about why this topic is so important. But what I want to do is leave you with some things to think about and some places for action. So with that, I'll start the talk. we know that the world is in a race to get to net zero emissions. And the big question that everyone's struggling with is, how can we get there? If you look in the news of late, there is a lot of discussion, and 5 of the major companies have made net zero commitments. Shareholders and investors are pushing companies to make those type of commitments. So what does net zero mean? And why? Why are we seeing that pressure? So number one, there is a big belief that we are in the crisis of our lifetime. This temperature rise is creating all kinds of issues, and we've just seen that recently between the floods in Europe, the fires in California and in Australia. 2021 has been the warmest the planet has been. 70% of those under 18 believe that it's a global emergency, and 60% of the people over 60 believe the same thing as well. What is impacting our industry significantly is trillions of dollars have now been set aside to only get invested in companies that are in the transition and doing something about emissions. And certainly we're seeing a big focus on ESG, which really is the environment, showing the social impact and also governance. Along with that, the advancements we've made in detection technology is also starting to show how big the problem is around emissions for our industry. When people talk about net zero, I mean, there's lots of discussion around what it means. So I believe in this talk, I'm going to focus on it, meaning that we either emit no greenhouse gas emissions, or we try to offset our emissions to achieve that net zero. Now, there's a lot of narratives going on right now. So one of the ones that you'll hear a lot is that natural gas is not the fuel of the future because of methane, it is actually dirtier than coal. You've got a whole bunch of environmental groups going, the future is leaving oil and gas in the ground. We should shut down all of our oil and gas production, and we'll get all of our energy from solar and wind. And I'm going to talk about that in a second. At the end of the day, we're also seeing a lot of pressure on investment not going into the oil and gas industry, because the view is that our industry is contributing to climate change. And if we invest in it, then we're going to continue to have this temperature rise. The problem with all these narratives is that they are false. But the problem is, as they take hold, it's actually going to cause us to make the wrong decisions for our planet and for future generations. I found this a very interesting fact, and it's actually a slide. I apologize, it looks old. It's actually a slide from my 2010-11 Distinguished Lecturer discussion. But one of the things that amazed me was every day, we use around 32 billion barrels of oil. I mean, every year we use around 32 billion barrels of oil. That means every second the world consumes 1,000 barrels. By 2100, we will have over 11 billion people on this planet who are going to need food, clean water, clean air, and are pushing for this higher standard of living. What that means is our demand for energy is going to continue to go up. In addition, we currently use 3 times that amount from an energy equivalency point of view. And the phrase that was coined to represent this 32 billion barrels that we use yearly, it's referred to as a cubic mile of oil. And in total, our planet currently uses 3 of them. If we were to replace that amount of energy, I thought that it was quite interesting to look at that. And the source of this infographic is the oil drum, and it was a group of professors. What they said was, just to replace the oil we use, we would have to put in 91 million solar panels every year for the next 50 years just to meet our current oil usage. Alternatively, we'd have to put in 32,000 wind turbines every year for the next 50 years just to meet our current energy use. As you can see, a lot of these are going to take a lot of dollars, but it would take us over 50 years to try and meet the energy needs that we're currently using. So when people say, oh, we should just shut in the oil and gas and get all of our energy from renewables, I don't believe that that is truly feasible or realistic. This next slide looks at where we get all of our energy. So on the left-hand side, what you can see in that graph is 75% of our energy currently comes from oil, gas, and coal. By 2035, it will have increased and still be a very significant portion of our energy mix. Yes, renewables, hydro, and nuclear have increased, but they have increased at a far smaller scale than our demand for oil and gas. So when you look at the graph on the left-hand side, it does show a bit of a decrease in oil and coal, but more importantly, it shows us continuing to increase in gas. Additionally, when you track the world energy use and follow that molecule, I found this quite interesting. At the end of the day, from all our different sources of energy, at the end of the day, we're wasting 60% of it through waste heat, energy efficiency. So between our demand and how we use it, I think that there is an opportunity to look at the efficiency. According to the World Bank, the oil and gas industry alone flares over 14.5 billion standard cubic feet every day. It's attributing 35% of the world's GHG emissions coming from that. Now, they have just focused on associated gas. When you look at the data from the International Energy Agency, they estimate that over 79 million tons of methane is emitted, equivalent to more than 2 billion tons of CO2. Kairos, a group out of Europe that has been analyzing satellite data, says that they see a lot of non-routine flaring, and they see 15 occurrences every day from maintenance, which they're estimating contribute about 1 gigatons of CO2 equivalent. You can see from this that we've got all kinds of different pieces of data. And really, I think we've underestimated our emissions from all the different parts of our value chain. By underestimating it, we've missed an opportunity truly to tackle the low-hanging fruit that solving and eliminating methane emissions brings to climate change. So we know that methane has a big impact and that it's 86 times worse than CO2 over a 20-year period. Over a 100-year period, it's 25 times worse than CO2. And the problem is, as it lingers in the atmosphere, it starts to break down and eventually forms CO2. But in the process of breaking down, it emits VOCs and ozone and forms other toxic compounds. Because a lot of our goals and targets are the next 20 and 30 years, the fact that methane is 86 times worse than CO2 points to the fact that this is what we should really focus on. I got asked when I was doing this talk in Europe to talk about what could the impact be globally. And so I'm going to pick the World Bank number, and I've made some assumptions. I've taken that 14.5 billion standard cubic feet a day that's flared and vented, and I've assumed 65% is flared and 35% is vented. And I'm assuming here that a flare is 80% efficient and the stream has around 80% methane in it. What it says is that if we could cleanly combust these streams and ensure that there's high efficiency, it would cost us around $3.6 billion. We would reduce GHG emissions 2.6 million tons of CO2 equivalent a year, or 1 gigaton a year. Over a 10-year project life, it means that we would have reduced our GHG emissions, or our CO2 equivalent, at a cost of less than 50 cents a ton. And I want you to remember those numbers because I'm going to refer to them later on when we talk about some of the opportunities to reduce GHG emissions. This next slide is an interactive that MIT put together. And what they were looking and saying is, what are our opportunities to stop this temperature rise? So on the right-hand side, you see the graph with the projected temperature rise. And what the blue line shows is what are our opportunities. Now, I couldn't figure out how to keep it interactive in PowerPoint. So what I'm showing you here is I moved and played around with the different toggles. And what it shows is under energy supply, all of these didn't have a great impact. So getting rid of coal, oil, natural gas, you know, and putting in more renewables, those really didn't have the impact. What had the big impact was energy efficiency. So if we could improve our efficiency on transportation and our efficiency on buildings and industry, we had a greater impact on reducing the temperature rise. So it wasn't electric cars and electrifying anything, it was being more efficient. And what was interesting is focusing on energy efficiency also reduced our usage and our demand. So we indirectly got to lower usage of energy by looking at energy efficiency. When we look at emissions, planting trees or stopping deforestation didn't have much impact. Carbon capture didn't have much impact. What had the greatest impact was dealing with methane. And of course, those were all incentivized by having a carbon price. So if we look at our industry and look at where are the sources of methane, what you'll see is that we have emissions all the way from our wells to in the drilling, completions, production operations, all the way to the distribution to consumers, whether it's in our gas processing or our equipment, or in leaks or our maintenance. It comes from tank vapors, valves, pneumatics, and compressor seals. And you'll see a lot of conversation around this component. But I believe that's less than 5% of our emissions. The big emissions come from well unloading, for example, well testing, flowbacks, workovers. I've been in some conversation with folks in Australia, actually, where because of the risk of forest fires, there's a lot of venting occurring, which I think would be a great opportunity for us to reduce GHG emissions significantly. And we'll talk about that in a sec. Our compressor stations, our pipeline maintenance and facilities all have maintenance requirements, all have upsets. When we start up an engine compressor, when it's gone down, we usually do a soft start, which means we are venting the methane to unload it. And then finally, we know that a lot of abandoned suspended wells are leaking methane as well. Now, what's been interesting in the last little while is all of the different tools that are available now to start to detect our emissions. And I've titled this slide, really, There Is Nowhere to Hide. As satellites get launched and planes and drones are available, what they're showing, and this is a quick project in the Permian, what it's showing is all the sources that we currently have of methane emissions. And what was interesting, it also showed that there was a lot of flares in this case that were unlit. 10% of the flares were unlit and venting methane. The elephant in the room is we don't talk about these bigger emissions. We also assume that a flare is 98% efficient. And what I'm showing in the picture below is a flare camera, which is able to look and detect methane emissions. So what you see reflected in the lens of that camera, a flare, it looks lit. But when you look at what's coming off that flare to the picture on the right-hand side, you can see that there is a very large amount of methane escaping unburnt. So even though the flare is lit, most of that stream is escaping unburnt. And so when we assume and don't look at the flare and assume it's 98% efficient, we're actually missing a very significant portion of our emissions. We had a chance to work with Shell, and this was very early days. It was 2000, where they were starting to look at efficiency. And there was a lot of work that was done in Alberta around a flare. And what they were finding was the efficiency of a flare wasn't one number. It ranged greatly. It depended on the direction of the wind, the composition of the gas, the size of the droplets in the stream coming to a flare. All of those had significant impact, and the efficiency could be as low as 20% when it was a low heat content gas. So Shell did this testing out in the field to look and see if they could use enclosed combustion equipment that could handle high volumes, handle changes in throughput, and of course, in this case, they also had hydrogen sulfide gas. So could we, in this case, combust it cleanly, turn it into SO2, but make sure we didn't have any impacts at ground level? And of course, what you're seeing in this test was, yes, it was possible to have complete combustion with high volumes of rich gas. Later on, that turned into an opportunity, and the regulator, both in Colorado and North Dakota, when clients use this clean combustion equipment, are able in their emissions reporting and air quality permitting, if they use this clean combustion equipment, they can assume that it's 100% efficient. And we recently achieved ISO 14034 certification. And this new ISO standard is a standard for environmental technology, and it verifies combustion efficiency and the methodology to determine emission reduction. And recently, the Solar Impulse Foundation had picked clean combustion as one of the 1,000 solutions that will have the greatest impact on climate change. So I'm going to switch and talk about why should we look at routine and non-routine flaring and venting. So it isn't just about climate change. I think this plays a very big role in looking at sustainability, looking at energy efficiency, creating that social license with community. I mean, we see many communities pushing for moratoriums or tougher rules. And I think at the end of the day, it's also making sure that we're doing the right thing. So when you look at a flare, it's typically black and smoky. What that flare is showing is it's releasing volatile organic compounds, hazardous air pollutants, particulates, and of course there's methane slip in it. So it has not only an impact from a climate change point of view, it's got an air quality impact. The next part of this discussion is community. No one wants to live next to a flare. And we know that a lot of facilities are usually located in poorer communities. So it has an impact in terms of social justice. And in this picture, you're actually seeing a unit in a playground. So in Colorado, the DJ Basin is in the middle of Denver. And so it's a fine line to find that balance between industry activity and community well-being. The other reason to look at it is really around safety and opportunities to reduce your operating costs and capital. And what you're seeing there is a rail car loading facility. And then the final piece is around energy efficiency. When you think about the fact that we're flaring and venting over 14.5 billion standard cubic feet a day, that energy could provide enough energy for a third of Europe. And we've been wasting it every day for the last 50 years. I'm going to talk first on non-routine because I think that this is the area that we totally underestimated our emissions. So in this case, the picture you're seeing is an example of pipeline maintenance or pipeline blowdown. You also see the unit is in the middle of a whole bunch of houses, and a lot of the research work that was done by TransCanada, which is a large pipeline company, showed that it was possible, instead of venting on a pipeline blowdown, by combusting, and it was possible to reduce GHG emissions at a cost of less than $2 a ton. The next picture is a drone picture, and you can see the houses close by. And what you see in this picture is the ability to burn about 5 million standard cubic feet a day without a big visible flame that has tons of radiant heat. I know from the discussions that I'm starting to have in Australia is because of the risk with forest fires, everyone has been very uncomfortable to have an open flare. So this becomes a great alternative to eliminate that, but to also have a guarantee that there are no harmful emissions coming off the stack. The work that was done around noise showed that at 80 to 100 feet, the road noise was actually greater than the combustion of 5 million standard cubic feet a day. It also showed minimal impact in terms of temperature. And we all know that you cannot, if a flare was burning 5 million standard cubic feet a day, it would have to be placed far away and you would have an enormous amount of radiant heat, which of course would create a safety issue, especially in dry conditions. So when you look at cleanly combusting and not flaring, and by doing it in an enclosed system, you also create this opportunity to have low ground level heat radiation. In addition, it gives you an opportunity to do something with that heat, and we can talk about that in a second. There's equipment that's portable, easy to set up. In this case, what you're seeing is a patented hydraulic trailer that clips onto a unit, and it has the ability to set this unit, which is 40 feet tall, 12 feet in diameter, set it up in place, ready to go in less than 10 minutes. When the unit needs to be moved to another location, it clips onto it, lays it gently down on the trailer, and moves it to a new location. So there is technology out there that can accommodate the non-routine. When you look at opportunities around pad sites, this is a pad site in Colorado, in the DJ Basin, 44 well pad site. But what's important here is the technology allowed them not only to reduce the lease size by 30%, but it dropped the capital costs by about 25%. And when the regulator here recognized the improved performance from an emissions point of view, because Colorado is a non-attainment zone, and Denver is a non-attainment zone, it brought them well below their limits on VOCs and hence allowed them to increase production. And they were able to increase production at this pad site by around 400 barrels a day, which meant an increase of revenue of around $20,000 a day. In the gas processing side, lots of opportunity for innovation. What you're seeing there is eliminating water handling and condensing to deal with still column vapors. The vapors all come into this combustion device, and it guarantees 100% destruction of BTEX, eliminates all the expensive operating costs with water handling and water disposal, and ends up with a less than 6-month payout in addition to generating offsets and improving air quality. In this case, this is a compressor station with 325 million standard cubic feet a day dehy glycol dehydration. Here, they looked at a large size unit to eliminate all flaring and venting. So this unit has a dual purpose. One is to handle the day-to-day volumes, but the other is to deal with the maintenance and blowdowns and upsets. So in this case, all their engine compressor maintenance came to this unit as well as the day-to-day. So it is possible to create a site with zero venting and flaring. And I'm going to go through these really quickly just to give you a sense of, its fugitive tank vapors have solutions. Gas processing, in this case, it's the Eagle Ford and it's sour. Rail car loading, a sour gas processing plant. And then what I want to talk about very quickly is the opportunity to take that waste heat, because you're in an enclosed system, and generate power. Whether it's in oil and gas or in, processing or refining, we've got a lot of low-grade waste heat that oftentimes we're using aerial coolers to eliminate, where we could instead use it to generate power. And what's interesting there is a lot of regulation are starting to see the conversion of waste heat to power is green power with zero emissions. And what's nice is it's small footprint, there's zero emissions, and the battery is really simple. It's a hot water tank, and of course with small footprint. The opportunities there are not only to do that with flared or vented gas, but it's to pick other industrial low-grade waste heat, or pick up the heat off a turbine or a recip engine and generate additional power by making them more efficient. I wanted to illustrate this next example because one of the concerns everyone always has is, how do we finance these kinds of things? And sometimes we believe that we've got to choose between a strong industry or environment. And what I want to do by going through this example is showing it's possible to get to net zero, but to do it in a very cost-effective way. So this is a small battery. It's around 300 MCF a day. I'm going to assume the flare is 95% efficient for this discussion. But by cleanly combusting and getting 100% efficiency, we would reduce greenhouse gas emissions 2,200 tons a year. If I take that waste heat and generate 200 kilowatts of power to run that site, we reduce GHG emissions another 1,000 tons of CO2 equivalent a year. Because I'm generating power, and I'm going to assume the price is 8 cents a kilowatt hour, this generates a revenue of 140,000 a year. So whether I'm replacing pulling power off the grid or putting it onto the grid or eliminating diesel power generation, I've now got power to run the site. So if I look at a 10-year project life, my capital is about $1 million. The revenue I generate from offsetting my power is around 1.4 million. We've reduced GHG emissions 32,000 tons over the 10 years, which means we've reduced it at a negative cost of $13 a ton. Now, we can probably sell the offsets that we create here on the voluntary market. And for the sake of this discussion, I'm assuming it's $50 a ton because that's what our carbon tax is in Canada. That's another 1.6 million of revenue, which means that investment in technology generates a return on investment of over 100%. With a strong voluntary market, because everyone's trying to figure out how to get to net zero. And like I said, we can either have a site with zero emissions, or we can buy these offsets to offset the emissions we can't quite get to zero. This market is starting to grow. And what I'm showing here is an opportunity to create that in our industry. We've talked a lot about the methane piece, so I would be remiss in not mentioning, because this is a closed system, there's also an opportunity to pick up that CO2. Now, we believe that there's easy things to do because methane is so much worse than CO2, that if we can focus and get 80% of the way, thereby making sure we don't put methane into the atmosphere and we improve our energy efficiency, it buys us time to then do some of the tougher things like capturing the CO2. I want to share this next slide because there's a lot of conversation on carbon capture. And yes, we may need that down the road, but I believe we should do the easy stuff first. And I just want to show the economics around carbon capture. So in Canada, we've done 2 projects. One is Boundary Dam, which is a power plant, and that project cost around $1.5 billion to reduce GHG emissions 1 million tons a year. The other project we did was Questor, which is another carbon capture project in a petrochemical facility. It cost around 1.35 billion to deliver 1 million tons of CO2 equivalent reduction a year. As you can see, those are both very expensive from a capital point of view. In comparison, this methane abatement project in Mexico was 13 oil battery sites who were venting all of their associated gas. So for $8.5 million, they were able to reduce their GHG emissions 450,000 tons a year by cleanly combusting and not venting the methane. In addition, that $8.5 million included 3 waste heat to power systems generating 200 kilowatts at sites that had enough gas to generate that power. So for $8.5 million, we reduced GHG emissions 450,000 tons. So if I scale that to 1 million tons a year, it would cost $20 million. As you can see, this becomes a very, very cost-effective way. I would rather spend $20 million than $1.5 billion. So methane abatement is truly the low-hanging fruit. And as we look at the voluntary market developing, I think there's a big opportunity in Australia, especially because there is so much venting going on that by cleanly combusting, we probably create a very, very strong business case to reduce the GHG emissions. And once again, 80% of the emissions are coming from 20% of the sources. So if we focus on the big stuff, which is flaring and maintenance, I think we've got an opportunity to make a big impact and really reduce that temperature rise. These are some quick examples because I think this is a piece that becomes very, very important. How do we create the win with community? And as soon as you have a big black smoky flare and people are concerned about the odor and their safety, you lose the chance to change a narrative with them. And I think this is important. And oftentimes you'll see issues like moratoriums. And then finally, as the world gets more and more focused on emissions, with data and with control over combustion, there's an opportunity to demonstrate with continuous emission monitoring that the site is net zero or zero emissions. So in conclusion, I'm hoping that I've illustrated a cost-effective path to get to net zero. And really it is around focusing on eliminating flaring and venting and looking for opportunities for energy efficiency. In some ways, what I'm talking about today is counterintuitive. So changing one greenhouse gas to another, i.e. methane to CO2. But it really, because methane is so much worse than CO2, makes sense. I truly believe that natural gas is our fuel of the future, but we've got to deal with the methane. If we allow ourselves to continue to emit fugitive methane, the narrative that it's dirtier than coal will stick. So we've got to do something. And data has changed the game. We can't greenwash. We can't hide away. There's going to be nowhere to hide. It would be better for us as an industry to be proactive than wait for this news to come out. And there are technology solutions that will get us 80% of the way, and they don't cost that much. And I believe that this is our time for courage and leadership. And if we don't deal with emissions, I think it is a human rights issue. I think we've got the opportunity to create the future that our children deserve. And I really want to thank you guys for giving me the time to tell this story. And we'll open it up for questions.
Okay, thank you very much, Audrey. Right on time, that's great. Just before we go into Q&A, I wanted to ask a couple of quick questions by poll. So I'm just going to launch that now. People should see it on their screen. If you can just answer that, please, it would be great. I'll just leave that running for a few more seconds. We're up to about 80%, which is pretty good. Okay, so 90% voted. going to close that one. And then the second one is really just about us in Australasia. Are people interested in future online meetings held across the entire region? So of course that doesn't apply to you, Audrey.
I could see I couldn't vote.
Oh, I did open it up for you. So.
Oh, did you?
Yeah.
I know I've been chuckling because I've had this opportunity to do this talk, you know, and I was sharing with someone, you know, I had a chance to speak in Austria and, you know,
Right.
Romania, and I've got all these exotic locations, and they're going, oh, that sounds wonderful. And I said, yes, I'm doing it all from the chair in my office at home.
Okay, so I can share the results. I mean, that was 100%, obviously, and the other one was quite interesting as well. Okay, let's see if there's any questions. If anybody wants to raise their hand. So I'll go to the Q&A bit first. First one from Nathan. Sorry, that's me. How does methane processing / flare reduction work in emergency blowdown situations?
So, I mean, in an emergency, and I think it was the one picture I showed, you've got to look at the site and go, I'm going to have emergencies. And so that one site that made a commitment to the community that there would be no flaring or venting, designed and had the equipment ready to go. So ESDs are tied into it, PSVs, and routine maintenance. So you've got to plan it. If you've got a, you know, if you've got a planned outage, you can certainly bring in some portable equipment to deal with it, or you've got to set up your site in the same way that you think about flaring as your outlet or venting as your outlet. You've got to look and say, you know what, I'm going to design it with clean combustion equipment.
Okay. Another question here. Have you looked into the scenarios of collecting and recycling emitted gases, like injecting them back into a reservoir instead of combustion?
Yeah, and I mean that happens, but you've got to have the reservoir. You've got to have some sufficient volume to have that make sense. If you're in a facility or you've got a field development that has no pipeline infrastructure, certainly, you know, that is done and can be done. I know it's done offshore, but if you're looking at facilities where it's not practical or economic, where you'd negatively impact the reservoir, then, and if you're flaring and venting and really, you know, that volume I talked about that the World Bank has been estimating, that's been going on for 50 years, right? So how can we make sure as we do flare and vent that we're doing it in the cleanest way possible, and can we use that energy to either power the site or put power on the grid or provide it to a community close by?
Okay. Next one is, how dependent on the economics is a carbon price? We don't have one here in Australia, so should we have one?
Well, actually, a lot of what I talked about isn't dependent on a carbon price. Sorry, I'm going to move my camera. I just realized it was still on my presentation screen. So, you know, in the case of a DHI, it's reduction in operating costs. When I showed the pad site in Colorado, yes, regulation drove it, but air quality regulation drove it. So a lot of times we look at the impacts on VOCs on human health, the nuisance, or having a moratorium. The business case can be made by social license, so being able to drill that well, or the impacts on human health and reducing the costs in terms of hospital care.
Okay. Let me just flick through this right now. So Is the methane reduction opportunity greater in some countries, areas than others? E.g., would I expect onshore is cheap, and how about offshore opportunities?
So yeah, onshore is cheap, but we are having discussions with the folks offshore, because I guess the challenge offshore, especially if you've got a platform that's flaring, is you've got to put in a water curtain to protect the platform from the radiant heat from a flare. On some of the processing platforms, you're using a lot of fuel gas to get rid of, still column vapors, for example. So all the same processes that we have onshore apply offshore. Now the challenge is always spacing. But I think as the world starts to focus on the emissions coming from offshore, I think there'll be an opportunity not only to deal with emissions, but to look for opportunities on energy efficiency. So if we can generate power from waste heat, instead of looking at diesel or other ways, I think there's a big opportunity to reduce costs.
Okay. We did have a quick chat about Australia before the talk started. There's a question here.
Mm-hmm.
Do you know if the required equipment for abatement is readily available in Australia, or is it quite specific right now to the US and Canada?
So we have units all over the world, actually, but we've got a big rental fleet in North America. But we do have units in Indonesia and Thailand, and we're in discussion with some major players to look at bringing units into Australia, because I think everyone's starting to look at, options around venting the methane. So it's something that I'm very actively in discussion with, and would very much, love to continue that conversation, because if we can make a strong business case, then we're certainly very, very open to do. And I think the big opportunity in Australia, especially because so much of this stream is being vented, is that we could create offsets for the voluntary market. So you wouldn't have to have a carbon trading system in Australia, but you could sell those emission reductions to others that have to meet their net zero.
Okay. Yeah. Okay, we've got I think it's more of a comment, but you may wish to reflect on it, Audrey. So with reference to the renewable energy efficiency, I reckon we underestimate the future developments and innovations in renewables. All of our assumptions are based on current efficiencies to be the case in 2030, 2035, 2040, etc. However, like other technologies, renewables will also develop and replace the fossil fuels much more quickly than is anticipated. So those 32,000 wind turbine and 91 million solar panels equivalent to today's fossil resources is just a simplification. Hence, the oil and gas industry have to act faster to come up with more efficient energy solutions.
I agree 100%. And like I said, that was an old slide, but the way that I look at us dealing with emissions and energy efficiency is it buys us time. I think I was in a discussion today, and we've seen significant temperature rise, even this year. Canada, we're experiencing a heat wave that we're over 30 degrees, which we usually have 3 or 4 days of that in our summer. So someone was telling me that there's a concern that we will hit the 1.5 degrees by 2027, which isn't that far away, right? So I look at a lot of the things that I'm talking about as easy to do. The technology's already there. It could buy us the breathing room and the time. And that would give us time to improve renewables and do the R&D on other things. But right now, sometimes I fear that we're so busy on the moonshots and doing the R&D that we forget that we've got a problem right at hand right now, and we've got to do something.
Okay. Just before I forget as well, and there's more questions to come. A few people have asked about watching the recording again, which is positive, I guess. The SPE does make a recording of this, and I believe they will send out a link tomorrow. Obviously, the SPE doesn't have a record of everybody who attended, but I think what's best for me is I can distribute it to the section officers in the various sections across Australasia. So hopefully that answers the question to those who have asked it. Another comment in question here, excellent and thought-provoking presentation. You mentioned, Audrey, that we need to educate industry, society, and politicians. Have you managed to present this work to the senior executives at oil companies?
No, so we do have, I find in the US, there's much more openness to have this conversation, but what I'm finding is there's a conversation on net zero, but a big gap between what's actually happening. So I think we're still in the stage of aspiration, but we haven't got to actually doing something. So I think one of the reasons that I really saw this as a wonderful opportunity is a chance to influence the people that do the designs and do the work. You know, the folks at SPE, and I'm hoping that they will be the agents of change that push the day-to-day change, because it's really about adoption. And I think sometimes, you know, senior executives, you know, have this wonderful, yes, these are our goals. That's what they tell the investors. And it takes a while to translate into day-to-day and action.
Okay. I mean, this may be a little bit related. With methane abatement being significantly cheaper than CCS, why do you think there is still significant investment in CCS? With, for example, Shell recently announcing a project in Canada. I mean, perhaps the implication is that a lot of people don't really know about this.
Well, I mean, so this is my personal opinion. It's a magic silver bullet, right? And if you look at all the news, all these big companies saying this is the magic silver bullet we need, but it's going to be really expensive and we need all kinds of government funding. And I think in some ways, people treat it as a get out of jail free card. If I tell people, look, I'm working on it, and by 2050, it's going to be carbon capture, it means we don't actually have to do something now. Right. And I think it's unfortunate because I think we're putting our eggs in a basket that's very unproven. And because we've got such a big crisis at hand, we should be doing the simple stuff first. Let's get 80% of the way there. I've shown you very huge numbers because methane's 86 times worse than CO2. Trying to do carbon capture is picking the toughest thing first. Because reality is you're trying to reverse entropy. And in some ways, you define the laws of thermodynamics because you've got to put a whole bunch of energy in to capture that CO2 and compress it and put it down into the ground. And a lot of our unknowns are, will it stay there? What's the impact? And, you know, I saw the news article just today on Chevron's carbon capture and the struggles that they've had in Australia with carbon capture. So I keep looking at it going, it's expensive, it's got all kinds of operational technical challenges, yet that's where we're putting all our money. Why wouldn't we put the stuff that's easy, that's proven, that we know we can deliver on, that buys us time? And I think my fear is if we continue as an industry not to tackle this head on, we will leave our assets stranded. Trillions of dollars have been pulled away from our industry because we're burying our heads in the sand a little bit. I think this is our time to be practical and do things that make business sense and technical sense.
Mm-hmm. I mean, just leading on from that, Audrey, do you think there will be much improvement in the cost of efficiency of CCS? I mean,
no.
Granted all these pilots, etc.
No. Maybe we'll improve it 10 or 15%, but compression is compression. Capturing it, sucking it out of the air, or capturing it off of, I don't know what breakthroughs we're going to have that'll be absolutely amazing in the next 20 years. So we may make improvements in the 10 or 15% range, but not the improvements we, the example I showed you, I mean, we're reducing GHG emissions at a cost of less than $1 a ton. CCS is over $1,000 or $2,000 a ton.
Right.
Right.
Mm-hmm. It's interesting, yeah, for sure, especially with all the investment to date. You showed some portable enclosed combustion technology. Does that mean it can move between the sites as and when required?
You betcha. So that trailer is a patented trailer, but when people look at it, they find a hard time believing that it can pick up a unit that's 40 feet tall, 12 feet in diameter, and weigh over 40,000 pounds and set it up in less than 10 minutes. One of the things that was important to me was equipment has to work well and it has to be easy to use. And when we invented and built that trailer, that's what has got a lot of people excited, because there's no pickers or cranes, so we improve safety, we reduce costs, and it's just really designing it to meet whatever transportation or road conditions we have to accommodate. So in North America, I know it's different in California and Pennsylvania because they've got narrow roads. So my big unit doesn't work there. The unit that's 8 feet in diameter works better than the 12 feet in diameter.
Okay, safety related question. Is there any risk from high temperature combustion, as the units will be at ground level compared to a conventional flare stack?
There's significantly less because our chamber is lined with refractory. So I showed you the picture of someone standing at the base with a unit that was doing around 3 million standard cubic feet a day. You couldn't stand under a flare doing 3 million standard cubic feet a day. Even if you built it at 200 feet tall, you've still got that radiant heat. So because we're enclosed and we've got refractory inside, we also can flash arrest the air intakes. It becomes a zero risk of having a spark, creating a forest fire.
Okay. Again, there's been quite a few people who would like to see a copy of your slides. In our chapters here, we do ask the speaker if she can provide, if necessary, a sanitized version, and we put them on the website or whatever. So we can sort that one out afterwards. Audrey, I'm just letting people know that it should be possible.
Yeah, I'd be delighted. I'd be delighted to, and I can put my email address in the chat if anyone wants to follow up. So I'll do that as well.
Okay, I think I've covered most of the questions. Do you think this work would have progressed without a CO2 emissions tariff?
Oh no, because I've actually been at this since 1999. I retired from the oil and gas industry. I tried to be a stay-at-home mom, and by September I realized that wasn't going to work. And because I've been amazingly lucky in my career, I decided to focus on flaring and venting, because I put in flares and I've been at sites with black smoky flares. In 1999, everyone said I was crazy and no one would ever care about emissions or environment. But we built a great little company because I truly believe anything you do has to stand on its own. It has to make business sense. It has to have a value driver. Otherwise, it's not sustainable. So our growth from 1999 to now has been without subsidies or carbon taxes or any of those things. We've done it through solid hard work and cash flow. And we're a public company, actually, so there's a lot of information about us out there.
Okay, I'll just find one more. I think this is probably our last question, Audrey.
Okay.
It relates to the executives again. Any suggestion on how we can tie this recommendation, CH4 to CO2, in our overall corporate strategy to meet ESG obligations?
So I would be delighted to provide you with information, to have a conversation. I know that I'm in a conversation right now with Origin. They've hired a new sustainability leader who's who's very connected to their senior executive. So I started this journey very much about change. So I will provide support in whatever way I can help have that conversation at the senior levels.
Okay. Let me just do one final check. Oh, hang on, there's a few more have just come in.
And I did put an email there, sorry.
Big question, 2050 is only 29 years away. CCS is at its infancy and requires significant government funding. The clean combusting low-hanging fruit buys some time, but as you said, the world population will grow and energy demand will rise. Do you personally believe we will achieve net zero by 2050? Would we be better off accepting this will never happen and focus our energy on adapting with the extreme climate patterns going forward?
So I think we've got to adapt. I think net zero is not the complete focus that we should have. I think we should have a one on energy efficiency. Because when I showed you the slide, the MIT interactive, by improving efficiency, the fact that right now we waste 60% of the energy in a barrel of oil, if I can improve my efficiency by, let's say I take that 40% efficiency, and for the sake of making these numbers easy, and I improve it to 80%, I halve my greenhouse gas emissions right off the bat. And I halve the amount of energy I need to use. So I think, yes, we should focus on emissions. You know, it's great to have this goal of net zero, but I think we should also have a goal around energy efficiency. How can we develop our reserves in a cleaner way? How can we be more efficient? And at the end of the day, how can we as consumers use that energy more efficiently? Between eliminating methane and improving energy efficiency, that is our only path to stop this temperature rise right now.
Okay. I think that's a good way to end, Audrey. There's some other questions, all kind of a little bit similar to what you've already answered. I think that's a great job you've done.
Thank you.
So I want to say thanks to everybody who attended again. I've put a little note in there that I will revert to the various section officers across Australia that I've communicated with a copy of the slides that you're willing to share, and also a link to the recording if people actually want to see your talk again. And of course, last but not least, thank you, Audrey, for a great and inspiring talk. This Gaia Sustainability program is gaining a lot of momentum, and I'm sure we will hear from you again in the near future.
It's been my absolute pleasure, and thank you so much for inviting me to share something I'm absolutely passionate about. Thank you.
Okay, great. And I'll be in touch offline, Audrey. Thank you.
Okay. Thank you, guys.
Cheers.
Bye-bye.